The topic of my research is trajectory planning for a Quadrotor UAV with a suspended payload. The aim is to autonomously navigate a Quadrotor UAV with a suspended payload through a confined environment. This is an animation of the complete system designed in the project. The quadcopter follows the planned trajectory through the environment, successfully avoiding the obstacles. Through this presentation, I discuss how it was achieved. To reach the project aim, 5 objectives were identified. Obtain a mathematical model of the Quadrotor UAV with suspended payload. Design a flight control system for stable and controlled flight. Minimize the payload swing while controlling the UAV. Plan a trajectory through the environment. And finally, verify the performance of the complete system through simulation. Using the Euler-Lagrange theorem, a mathematical model of the quadcopter with a suspended payload is obtained. The Euler-Lagrange method derives a set of mathematical equations using the conservation of energy in the system. For multi-body systems, this has the advantage of directly giving a set of dynamic equations without the coupling forces between the different bodies. A flight control system is designed to receive horizontal and vertical force references. The force references are converted to a corresponding tilt angle theta and total upwards motor thrust U1. The tilt angle controller adjusts the moment induced by the motors to tilt the quadrotor to the desired angle. Two outer loop controllers, a proportional velocity controller and a state space position controller, are implemented. These controllers supply force reference commands to the inner loop system. To minimize the swing of the payload while controlling the quadrotor, input shaping is used. Input shaping is an open loop method which modifies the reference signal to reduce the oscillations in a lightly damped plant. Instead of applying a single impulse which will result in a lightly damped response, a secondary impulse is applied, with amplitude and timing selected to cancel out the response of the first impulse. For the quadrotor with suspended payload, if a velocity step is applied, the payload swings as the quadrotor accelerates. When a velocity command is modified, broken up into two smaller steps, the oscillations are cancelled out. Discrete path planning algorithms were investigated as a method to plan a trajectory through the environment. From an initial position, the algorithm applies the available actions to the initial state. The new states generated are stored in memory, for which the algorithm repeats the process for the stored states, applying the actions to the new generated states. The search algorithm continues in an outward manner until it reaches the goal state. A variation on this algorithm, the A-star algorithm, improves the performance by implementing an estimate of the cost to the goal region. States which are closer to the goal region are visited before states further away from the goal region, enabling the algorithm to obtain a solution quicker. The A-star algorithm is modified to plan a trajectory for the quadrotor with suspended payload. Instead of just the position of the node, the states of the quadrotor is tracked, such as the positions, velocities, and payload angle and acceleration. Instead of discrete up and downward movement, the next state is calculated by simulating force and velocity inputs to the flight control system. Two implementations will be discussed here. An implementation with a primitive action space and another with a complex action space. For the primitive action space, horizontal and vertical force commands can be applied for a fixed sampling time by the search algorithm. The action space consists of a no-force action, large and small horizontal force references, matching the amplitude and sampling time of the input shaping actions, and upwards and downwards force references. An implementation with a complex action space is also implemented. in which the search algorithm can apply not only force references, but also velocity references. Within the action space, input shaping velocity actions are designed to minimize payload swing. A horizontal force action is designed to avoid obstacles in the environment, allowing the quadrotor with a suspended payload to fit through an opening with a height less than the extended length of the quadrotor with suspended payload. What is more, the action space is sequence constrained, meaning if the current velocity is zero, it can only apply input shaping actions, no full velocity actions. The same if the quadrotor is traveling at full speed. The action space is limited to actions that will keep the quadrotor swing at a minimum, such as input shaping actions, or continue at the current velocity. The test environment consists of a tunnel with an obstacle, a vertical chimney, and finally a horizontal tunnel leading to a goal region. Both the primitive action space as well as the complex action space manage to plan a sequence of inputs to navigate the quadrotor through the environment. The planned paths in both cases avoids the boundaries and obstacles and successfully reaches the goal region. The path planned by the complex action space is much more controlled than the path planned by the primitive action space. This is verified by the payload angles of the planned paths. The payload swings in a much more controlled manner for the complex action space than for the primitive action space. The performance of the complete system is verified through simulation. When friction and drag is introduced into the system, the actual executed path falls behind the planned path due to the actual dynamics differing from the dynamics used to plan the trajectory. To combat this, a feedback control system is implemented. The current system applies the input sequences to the controller. The system is expanded with an additional controller, which compares the planned trajectory with the current trajectory, correcting for the differences in position. With this implemented, the executed path matches the planned path much more closely. The project successfully reaches the original project aim of autonomously navigating a Quadrotor UAV with a suspended payload through a confined environment. The best results were obtained by making use of a complex action space consisting of sequence-constrained inputs. Feedback control systems are needed to ensure the quadrotor stays on the planned path. Future work includes implementing the system for a specific quadrotor with payload and verify the performance with real-life flight tests. To implement the system in a confined environment without GPS signal, a simultaneous localization and mapping system needs to be developed. Looking at the animation again, the input shaping actions can be observed as the quadrotor starts and stops, as well as the obstacle avoidance sequence used to fit through the gap. Thank you.